Willkommen, guten Tag. We are having our second lecture by Manfred, but be careful that we have a tea just afterwards, but we'll take the picture today. So it will be at the beginning of the coffee break, so don't rush on the cakes. Just make the picture and afterwards we'll have the cake. The picture will probably be just outside here, but wait for confirmation. And please.
Thank you. I prepared a little bit, sorry. I want to review a few things and then do certain things rather quickly, and then maybe we have a bit more time to discuss some ideas. Yesterday we talked about the homospherical argument, the setup, and hyperbolic quotient, etc. And this argument, this homospherical argument that I explained, also proves a couple of other things. I just put them here. So one theorem that Fürstenberg proved some time ago, completely with different methods, is that if you have a co-compact lattice, meaning you have some discrete subgroup so that the quotient is compact, then the homocycle flow will be uniquely ergodic. So every orbit will equidistribute, and every orbit will equidistribute with an error rate that does not depend on the base point whatsoever. That's what I mean by the error rate. It's like the same estimate that we had yesterday for the periodic orbits. So if you flow for the homocycle flow up to time t, and you have your smooth test function, then the error will be t to the minus some exponent times the Sobolev norm of the function. Same kind of estimate like yesterday. Another theorem that follows by this method is Dani's theorem, which was a generalization of Fürstenberg, and Dani also relied on the method that Fürstenberg used, but it also can be done by the homospherical argument. If gamma is a lattice but not co-compact, like PS2Z that we discussed yesterday, then there are only two types of invariant and ergodic probability measures on the X. Namely, either if you have an invariant and ergodic probability measure on X, either it's a periodic orbit measure sitting on a one-dimensional periodic orbit of the homocycle flow, or it's the Haar measure of the three-dimensional manifold. So there are only those two types, and it again follows. There is some, in particular, that's not part of the statement, but you can also prove this. That's a bit more work. In particular, you can also show that any orbit whatsoever either equidistributes with respect to the Haar measure or is periodic itself. That's sort of an upgrade of this statement. It's sort of ideally it's sort of the combination of the two, because up here it was automatic that every orbit equidistributes. Here it's either you're periodic or the orbit equidistributes. However, there's some difficulty if you want to make an error rate, because you could be very, very close to a periodic orbit, and this could happen sort of frequently, again and again in the future, and that would sort of remove the possibility of having a uniform error rate statement. So that we would have to have some conditions on the starting point, some Diophantine-like conditions on the starting point to be able to give you an error rate for the equidistribution of non-periodic orbits. And the third one that I also mentioned yesterday was if you have a quotient, co-compact or finite volume lattice, it doesn't matter, and you take any point, so the x is some point in the space, and then you, didn't use the letter yesterday, then you multiply x with SO2R, which just rotates the vector attached to the point in the manifold around, and then you hit it with AT, which means you take these vectors and follow the vectors, then you get an expanding circle, and this expanding circle in the quotient that you're considering will equidistribute, and it's the same argument again that can prove that, and again it will be done, you will obtain this with an error rate if you use spectral gap from the space. Are there any questions about this page? Good, then we are happy with the homospherical argument, and I want to sort of now talk about other settings, bigger settings. So I'm, like also a little bit yesterday, I want to consider more general Lie groups. So G is a more general Lie group. Gamma is some discrete subgroup. Think SLNR modulo SLNZ, that would be a nice example. sort of the mother space of many, many, many other examples. And then let's take a unipotent, say one parameter subgroup. What does unipotent mean? Unipotent, G is unipotent if G minus the identity is nilpotent. Okay, that makes more sense in SLNR than in a general Lie group, because what does minus mean in a Lie group? So maybe this is the informal definition that you can remember quickly and is working very well for SLNR. But other than that, you just take the adjoint action of G on the Lie algebra. This is now a matrix. Now you can subtract the identity and require this to be nilpotent. Sometimes people say add nilpotent, but if the group is a general Lie group, there's no other meaning to unipotent than add unipotent, so just say unipotent. And one parameter is clear, should be just one isomorphic to R and consist of unipotent elements. Like our horocycle flow. Our horocycle flow was the prime example of this. Okay? And then one thing you could be interested in if you are interested in ergodic theory and dynamics on such nice homogeneous spaces is what are the invariant and ergodic probability measures on that space? And the answer that Marina Ratner proved after some other results of Margulis towards Oppenheim conjecture, which also related to things like that, is that any such invariant ergodic probability measure on the quotient is automatically homogeneous. What does homogeneous mean? Homogeneous means, I would even say algebraic, but maybe in this context, in this generality, I shouldn't say algebraic. It means that it's a H measure on an orbit. Mu is homogeneous if the support of mu is equal to x times L for some x in x and some subgroup L in G, and mu is L invariant. It's automatically ergodic because L is transitively on the orbit. So, yeah. It comes from a H measure. It comes from a H measure on the space. On an orbit. So, when L acts on X, there will be some stabilizer. This stabilizer is a lattice, and the quotient L mod this lattice is isomorphic to the orbit, is isomorphic to XL. So the measure is like the H measure that we considered on this big space, except that we now consider a suborbit, a smaller subgroup, and the orbit of the subgroup. Okay? Are there any questions about these two notions or the theorem of Ratner? It's also called measure rigidity theorem, because you would have expected to have way more invariant and ergodic probability measures, because usually you have way more invariant and ergodic probability measures. You usually have so many that it's very impossible to classify them. But here, voila, everything is sort of algebraic, everything can be classified in terms of group structure, and if you want to understand all of them for a concrete setting, of course you need to understand all possible L's that could pop up, and then find out which X's could have closed orbits for the L, closed finite volume orbits for the L that you want to consider.
You may have said this, but L is closed, right?
Yeah.
Yeah.
I didn't say what the symbol means, but obviously close is contained in the symbol. Thank you. If I go here with one parameter, then L is even a connected subgroup. I can choose L to be connected, because the group here is connected. The group here can also be assumed to be connected. Thank you for the question. Is there another question on the theorem? Yeah, this is not a cheap theorem. I mean, this This was a big deal. This is a landmark result of Marina Ratner. And I think if you have done sort of a little bit of homogeneous spaces and a little bit of ergodic theory, then you have another year ahead of yourself to sort of study the proof in a course maybe. Yeah, of course you can always compress it, but I think if you do it in a course it takes about a year, I would say. Okay, and there are many other theorems of hers, that's two that stand out very, very much in that spirit. If you have a starting point, any point in the space, x, and you let your u act, which is a one parameter subgroup, you let it act on this point, and you ask what happens to this orbit, well it equidistributes to a measure like this, and it equidistributes precisely the orbit closure to the H measure on the orbit closure, because the orbit closure is precisely a set like this. That's another theorem, that's the equidistribution theorem. And yeah, mixed in sort of the closure theorem. If you have a group generated by unipotence and you take the orbit and the closure of the orbit, it's always homogeneous with finite volume like this. So there are many, many, many nice things coming out of this. This is sort of the starting point of the logical argument. One starts with this. Okay, one other corollary which is sort of going a bit further in the algebraic direction is this corollary of Moses-Shah of Marina Ratner's results, and it's a bit in the spirit of the theorem of Sarnak that we discussed yesterday. And for many other applications, this theorem is kind of very, very useful. So what does it say? We have a measure, a sequence of measures that are homogeneous. They're sort of nice algebraic objects that look like H measures on orbits. There's a sequence of such measures. They are all invariant and ergodic for a unipotent subgroup. Or unipotent subgroups, they can vary, I don't care. And then you have the sequence of measures and you look at weak star limits. Maybe there are some subsequences that converge. So look at all such subsequences that converge. Any weak star limit is either the zero measure. We have seen an example like this for the homocyclic periodic orbits, because the periodic could shrink, the orbit could wander off to infinity and never come back, and then the limit measure is the zero measure, or the limit measure is a homogeneous measure, again of that nature, where the dimension actually goes up. And there's much more geometric information about this convergence, how it takes place, and that the relationship between the homogeneous orbit before taking the limit and the homogeneous orbit after taking the limit. What's happening is that somehow the equidistribution to the bigger homogeneous orbit is happening almost from inside. It might not be inside, but you can just push it a little bit, and then it will be inside, and it will equidistribute from inside the limit measure. So it's really a very nice geometric theorem, but it has no errors whatsoever, because it uses error rate statements, because it uses all the technology of Marina Ratner, which is sort of very much in the spirit of ergodic theory. Oh, you want to prove equidistribution? Okay, let's go to the limit and study what the limit is. That's sort of the natural method in ergodic theory, because the limit has many more nice properties than the measure you had sort of before you took the limit. Often this is the case. But by saying, oh, let's study the limit, you have forgotten what you actually want to study if you want to study the error rate, right? Because you're now just studying the limit and not any longer the distance between the object that you started with and the limit object. So today I want to outline a theorem in the direction of Moses-Shah, where we actually are able to give an error rate. there any questions about?
Yeah, quick one. These limits of invariant ergodic measure might not be ergodic, or they are automatic?
It would also be ergodic for a unipotent. It's not always the same, or it's not always the limit. Say your sequence was invariant on the same unipotent all the time. The limit measure may not be ergodic under this unipotent. But there would be a unipotent under which it's ergodic.
But this doesn't happen for SL2 because it's too small somehow?
In SL2, if you have a semi-simple group acting,
The
yes,
picture you drew
it's too
yesterday,
small.
just a
in yesterday's case, yes, it's just a coincidence that we will get an ergodic measure in the limit.
But in SL3 over SL3R, give examples?
Yes, because it contains the Heisenberg group, and I think in the Heisenberg group I can construct an example like that. Yeah. You can also, if you allow yourself to change the unipotent, I can give you a completely trivial example. So let's take the two totals, and let's take periodic orbits that are rational, but converge to the horizontal. Then in the limit you're not any longer ergodic under the horizontal direction, which is the only direction that you knew you were invariant to begin with. So it's really an easy thing that can cook up, and you can cook up. Okay. And in the Heisenberg group you can sort of mimic this behavior while, strictly speaking, having always the same unipotent along the sequence. Yes?
I wanted to ask, you said like in the Mottes-Schar argument there are no error terms because in Wagner's theorem you don't get error terms over Wagner's argument.
Yeah.
But like where could Wagner, like in Wagner's theorem, at least in the statement, nothing is converging.
Precisely. So this is
it's like an existence result. So
yes. So Ratner's theorem is effective because it's an equation, right?
yeah.
But that's not really helpful. You want to So the way I want to prove this theorem is I really effectivize some arguments of Ratner.
Okay.
Because I can only get sort of an effective version of Mottes-Schar by actually opening up the box that is the Ratner theorem.
Okay.
I need to mimic sort of the ideas a bit more than just say, okay, this is good enough for me. It's not true. Because in a way, what I do in the theorem to come is I study this measure before going to the limit. And it has sort of many layers like this. It has many layers. And then I say, oh, okay, it's really invariant. It's only under this direction. But because it has so many layers, it's maybe also almost invariant under this direction. And then I have a measure that's sort of almost invariant under R2. And that, in this case, already deals with everything. But if this would be embedded in a bigger space, I would have something that's like invariant under an intermediate subgroup. And it's then like a measure of that Ratner studies, but except it doesn't satisfy the assumption because it's not really invariant, it's just almost invariant. And then I have to look really at the proof and open everything and see whether I can use some of the ideas. And I can use some of the ideas, but only under additional assumptions, and not in this generality. Okay. An effective version of a special case. So this is joint work with Margulis and Denkadesh. And I'm not going to give you the most general thing, it's sort of the general theorem that we proved some time ago is not that general, and it would be a mouthful to even swallow the formulation because of the possibility of intermediate subgroups. Somehow let me just say it very briefly. If you work effectively and the intermediate orbits possible, it's unclear what's the limit really. Is it sort of this object? Right, you could, in the two drawers, you could have sort of lots of points lying up along a line. And then is the limit, the effective limit, the line, or is the limit the square? It's a bit unclear what it should be. So you can choose, and depending on your choice, you get a better or a worse error. If you choose the line, which is the small dimensional object, you get a better error. And if you choose the square, you get a worse error, but you get equidistribution in the square. So and that requires care and is a bit confusing, so read it, but I'll not talk about it further. Okay, I'll just consider a special case, and that's sort of a maximal case where there are no intermediate possibilities, which removes that issue, and I will even just talk about one case so that we have something concrete in mind. G is equal to S of 3R, gamma is equal to S of 3Z, H is equal to SO2 1R, so that's the stabilizer of the defined by x1 squared plus x2 squared plus minus x3 squared, say. So you have this quadratic form, and you look at all determinant 1 matrices that preserve this quadratic form, the values of this quadratic form, and 2 plus is 1 minus, that's the signature to 1 here. And then x equals the quotient G mod gamma contains many closed finite volume orbits xh in x. I'm just telling you that's sort of a nice other story. And we can, let me just add some information. These correspond to rational quadratic forms of signature 2, 1. Where if you, there's sort of a dictionary that you can build, the quadratic form and then the orbit. So if you take x1 squared plus x2 squared minus x3 squared, then this is just gamma h. Gamma h itself is a closed orbit, and you get this. But if you do something like x1 squared plus x3 squared, x2 squared minus 2x3 squared, then over rationally, sort of, you have changed the quadratic form significantly, because over the rationals 2 is not a square, this is not equal to that. They are not the same, unless I'm mistaken. Anyway, there are many examples, and if you change the quadratic form, then you have to put here a matrix in between that, and then this would correspond to that. This matrix is a real SL3R matrix that has the property that it moves this quadratic form to that quadratic form, or the other way around. So this G is sort of linking the two, and the H is always the same H that I'm using. It's always defined by this quadratic form. Anyway, not important. Just take it as a black box that there are many closed orbits inside the space, and that the volume actually can increase. So many means countable many. There are countable many closed orbits like that. Countable many orbits. In fact, we have countable many orbits. with volume going to infinity. It becomes more and more complicated as you move along the. If you keep changing the analytic form, you get more and more complicated orbits inside this. There are now three-dimensional orbits inside this eight-dimensional quotient. So we have three-dimensional closed orbits of this intermediate group, and our space is eight-dimensional. So, in fact, those are the only, that's the complete classification of the H-invariant anechoic probability measures. The H-invariant anechoic probability measures, when H acts on my quotient X, are precisely these countable many periodic orbit measures sitting on these closed finite volume orbits, and the Haar measure, the eight-dimensional Haar measure on the whole space. So that's sort of Ratner's theorem. Yeah. And now we want to ask this Moses-Shah question: what's happening when the volume changes? Moses-Shah will tell us, because of the extra geometric information, that if you have really a large volume orbit, it will be very close to equidistributing already in the space. So if the volume goes to infinity, these orbits equidistribute. Moreover, these orbits equidistribute. Because of Moses-Shah. And we want to ask, so can we give an error statement for that? And the answer is yes, we can give an error statement for that. And we want to outline how to prove this.
But you know that no subsequence goes to zero?
Say it again?
You know that there is no subsequence which goes to zero?
No, it doesn't happen in this case. Somehow the group doesn't fix any vectors and no planes and nothing. Somehow the group, the SO21 acts irreducibly on R3 and has no fixed vectors and no fixed planes. And that always rules out the possibility that it sort of could be stuck in the cusp. You cannot be stuck, you always move down as well. Good question, thanks.
And also the volume has to go to infinity. I mean, there's finitely many below any given volume.
Yeah, but in other spaces you could, that's what I said even.
No, that's There's only finitely many orbits beneath any given volume.
Yes, but I said with volume going to infinity, it's precisely the same.
Yeah.
Okay, Vierer. There exists some kappa greater than 0, so that we have, so we integrate a test function over a closed orbit xh, and we compare this to the integral over the whole space. And
normalized by the volume of the orbit?
of course, everything are probability measures. I'm in a logic theory, yes. Thank you. We have integral minus integral, less. Now, yes, this is normalized, but here I'm of course talking about the normalizing factor. So the volume is the normalizing factor. Volume xh to the minus kappa. The smoothness of the function again plays a role. If your function is crazy, then of course it can miss very easily the orbit. If the function is sort of having a bump function precisely in the gap, then no closeness will happen. But then it's the fault of your function and not of your orbit. And if it's a bump function that's sort of precisely in the gap, it will have to increase and decrease very rapidly, so the Sobolev norm will be large. So then we'll not get a contradiction here because this might be positive, this might be 0, but this will be large, so.
What do you mean by, sorry, the volume of XH? XH is a three-dimensional
Yes.
translate of this subgroup. So you normalize some measure on the
So
subgroup.
the H is a fixed group. I
Yeah.
fix my Haar measure on H. And then the XH is an orbit, but orbits are always isomorphic to group mod stabilizer. So I have a discrete subgroup in H that corresponds to X. And I have a fundamental domain
Quotient.
that sort of parameterizes uniquely the orbit. And I'm just taking the Haar measure of the fundamental domain and call this the volume of the orbit. So it depends on the fixed choice of the Haar measure on H, but H is not moving, so that's okay. And if I already have this fundamental domain on H, I can push the Haar measure on the fundamental domain down to XH, and that would give me a measure on XH, which is large, and now I normalize it by dividing precisely by this volume, and that's the measure that I consider here in this expression. Because it's in Moses-Shah, in Ratner, and over there, we always consider probability measures. So here we consider probability measures.
Yeah.
I crossed out the thing to note the average here. And yes, that's the statement. Now, what are the quantifiers over X for any closed orbit, closed finite volume orbit, XH in X, and any F in CC infinity. And the kappa is uniform, don't ask me about it. It's not so big. It's positive. And it's kind of, it's sort of a good structure of the statement. I mean, that it's polynomial, even when the exponent is not so great. It's sort of a polynomial error rate, just like we had it for the horocycle flow. Okay. So there are kind of 3 steps or so that we need to go through to have at least an idea of how to prove this. But yeah, the first step, also in the first step in Ratner's measure classification, is to say, okay, I want to study generic points. Somehow, if you want to understand a measure, invariant ergodic probability measure, it's sort of nice to study its generic points. So what's a generic point? A generic point is a point where that equidistributes when you do the dynamics. What does equidistribute mean? It means that for every continuous function, the ergodic theorem is true. And how do you prove that? How do you prove the existence of generic points? Well, you apply the pointless ergodic theorem. To any given function, you can apply the ergodic theorem. And then you say, oh, but the space of continuous functions of complex support is separable. So I actually only have to apply the pointless ergodic theorem to all the functions in the stance countable subset of functions, because if I know the ergodic theorem, that the equidistribution for these, then approximation will tell me the statement for all continuous functions. So I'm taking a union of null sets when I define generic points. We need to make this all effective, because we want to obtain error rates, right? So we need to make all these things effective. We need to have an effective pointless ergodic theorem that works for every fixed function, and then we need to sort of take, in some sense, an effective union of null sets to get an effective pointless ergodic theorem that doesn't depend on the function. So those are 2 steps that we need to do. Let's do that. First step, generic points. let mu be the H invariant probability measure on XH. Okay, I want to have an effective ergodic theorem. You have a question?
Are you assuming XH is closed here, or is it X?
Yeah. Closed final volume orbit XH, yes. That's by probability, yeah.
Ergodic theorem with respect to the action of what group?
Thank you. That U in H be a one parameter unipotent. You could also ask about bigger groups, but I want to somehow stay close to Ratner's ideas. Alex actually will talk about bigger group actions, and then he can tell you about ergodic theorems when actually H is acting and not just unipotent subgroups. But for me it will be unipotent subgroups that act. We already discussed a little bit how Moore, one ingredient of how Moore is Mortner phenomenon, and Mortner phenomenon tells you when H acts ergodically, for instance when it acts transitively it will act ergodically, when H acts ergodically, U will act ergodically. So I'm not losing any part of the measure theory, of the ergodic theory in some sense, when I go to U. That's sort of special. Usually this doesn't happen, but for the semi-simple group H, which my SO21 is, this is happening. SO21, by the way, is more or less SO2. Or it's actually more or less PSO2. Also not quite, because I should have taken the connected component, never mind. Okay. I need a pointwise ergodic theorem, which means I need a ergodic theorem, which means, and I need it effectively. Where could I possibly get that from? Well, mixing implies ergodicity, and ergodicity implies the pointwise ergodic theorem. So hopefully effective mixing, which is my spectral gap estimates, my decay of matrix coefficients estimate, will give me an effective pointwise ergodic theorem. Right, so that's what we want to do. So we need, again, the spectral gap. There exists some delta greater than 0, so that when I look at US, that's the parameterization of my U. Yeah, we call it pi US F, inner product with F, minus integral of F absolute value squared. That's the right expression. That is less than 1 plus absolute value S to the minus delta Sobolev of F squared. That's this estimate that we talked about yesterday, this effective decay of matrix coefficient, effective Moore theorem. But there's probably a question. Who wants to ask the question? Yes?
I mean, but I know the answer. So.
Yeah.
You're using Selber to make sure that delta doesn't depend on.
Yes, it's quite important here. I'm always using the XH.
Yeah.
I'm using the XH orbit, not the ambient three-dimensional thing. I want to study this measure, right? That's the H invariant measure on here. And hence I have this orbit XH. And I want this estimate. And I want this estimate in a way so that it does not depend on XH. Because in the end, I didn't emphasize it here, but I hope it was, no, it was actually written correctly, right? So this kappa here is introduced before I introduce the orbit. Obviously, I don't want this kappa to depend on the orbit. Because if the kappa depends on the orbit, this statement I can prove in 2 minutes. Because it's trivial, it's saying nothing. I just choose the kappa so that this is basically 1, and then this is the Sobolev-Benedict theorem. Meaningless. So, obviously I don't want any dependence on the orbit, except for this integral here, right? This integral and the volume, this is where the orbit enters, nowhere else the orbit is allowed to enter. Not in implicit constants, not in exponents. So this delta here, the spectral gap here, is not allowed to depend on the orbit that I'm considering. Because if it would, then probably this delta will at some point become this kappa. Then I'm doomed from the beginning. So I need this uniformity, and this is precisely Selberg or Jekyll-Langerhans, I keep forgetting. So in the compact quotient case, it would be
modulo congruence in this case, I think.
no, but I'm also looking at compact quotients of H.
Then yes, I guess it's Jekyll-Langerhans from Selberg.
Yes. So I need quite a bit of number theory to make this uniform, but it has been done. Where delta is independent of xh. So in some cases this is Selberg's theorem, 3/16, and in some other cases, in this particular case, I need to use Jekyll-Langerhans to update this to compact quotients as well. Which is kind of funny because compact quotients, to prove spectral gap for compact quotients I find easier, because compact quotients are somehow easier, except to prove the uniformity, I somehow need to use Selberg to get it. Or, say again?
Initials that you the name.
Spelling.
Yes.
CQ.
CQ.
UET. T. Okay. There's a T at the end of it. Okay. Langerhans.
This one is easy. Yeah. So we need that, and in more general cases we would need Cosell. So this has been done in great generality by Cosell, and it's called property tau. Property tau is sort of a little brother of property T, which sometimes little brothers make more trouble than older brothers, right? So it's way harder to prove.
If we understand H to be SL2R, then US is the usual unipotent, like 1 and 1.
U is the unipotent, yeah, upper unipotent. Nothing special.
I mean, if we understand H to be SL2R, like, or image of SL, H is like SO21, right?
Yes?
And if we understand H to be like PSL2R or something like that, then
Yes.
US would be just 1 as 1.
I mean, they're all connected.
Okay. Now, I want to get a point Poisson-Golding theorem. That's still the goal. I define a discrepancy function at a point as more or less this expression that we have written now. I'm integrating from 0 to t f of x us ds minus integral f d mu, which is my closed orbit xh. And I square this 1 out. So that's sort of testing how much the point Poisson-Golding theorem for this point and this scale t actually already holds. Right, so I want this to be small, then the ergodic theorem is good. So I want to know how big this is, on average in some sense. So I could just try to integrate this function, it's positive, right? So if I integrate it, I get to know how big it is on average. So I integrate this dt f with respect to my measure mu, and I need to integrate the square, but I can do the same calculation that Omri did yesterday. It looks a bit different and it may need Fubini at some point, but in the end what you get is integral over xh 1 over t, integral from 0 to t f of x us1 ds 1 over t 0 to t f conjugated x US2 DS2 so far so good, d mu minus integral absolute value f d mu absolute value squared. It looks wrong, but do the calculation more carefully, then it's fine. Because there's some mixed terms coming up, and the square term that you see at the end actually has a plus, right? But then because of the mixed term, it becomes into a minus after Fubini and so on. Homework. Now, here I do again Fubini, and I rewrite it slightly differently. I get integral from 0 to t, integral from 0 to t, inner product of pi us1f, pi us2f, es1, es2. I could even take this into the expression. ds1, ds2. So it's an elementary massaging of the integral. Fubini is the most difficult thing to use. And here we now see the expression for which we have an estimate. But not for all S1 and S2, right? The S1 could be close to S2. And if that happens, then there's no good estimate for this. So I need to look at the square and say, if I'm too close to the diagonals, then I have nothing. Well, I know it's bounded by the Sobolev norm squared when it's too close to the diagonal. And if it's further away from the diagonal, then I use my estimate. So what's the definition of too close and further away? T to the 1/2. I don't know. I don't care. Some exponent of t is the right thing. So let's just say we define here t to the 1/2 neighborhood of this square which goes up to t. So then this is somehow both things. It's very small, but it's also very big. Because there are infinitely many powers between t to the 0 and t to the 1, and we just use one of the powers between, and then we can sort of play with, oh, t to the 1/2 is very small, it's very small compared to t, but t to the 1/2 is very big because we think of t as very big. This kind of game just happens very often. So then we have that this is less t to the minus delta half s of f squared if absolute value s1 minus s2 is bigger than t to the 1/2. And then this whole thing becomes estimated by, okay, we need to estimate calculate the area of the strip, estimate the area of the strip here, which is t times t to the 1/2, that's the area of this, times s of f squared, because that's a trivial bound for both expressions when you are too close to the diagonal, and when this estimate kicks in, then we just estimate it by on all of the square minus what we had here, who cares, times the estimate t to the minus delta over 2 s of f squared. And then this whole thing is just t to the minus eta, let's call it free eta, s of f squared.
The t squared there should also have a 1 over t squared. Oh, it's outside, sorry.
There's one outside here.
Yeah.
And the t squared cancels, and this is good. And here I have t to the 3/2 divided by t squared, so everything has a negative exponent. Probably this guy wins and is the worst one, but I don't care. Okay? So this is saying that on average, because I integrate over the whole space, right, over the whole space with respect to my measure, on average, my discrepancy must be small because the discrepancy is positive and the integral is small. So on average, I must have small discrepancy. My ergodic theorem needs to be correct up to a very fine scale for this, when I average up to t. For many points it needs to be true. So the other thing I do is, I think it's called Chebyshev inequality. It's just a stupid measure theory trick that now allows me to convert this statement into some other statements. So I take the measure of all the x where the discrepancy is bigger than, let's just say, epsilon times the Sobolev norm of f squared. And then this Chebyshev inequality trick says this is less than epsilon to the minus 1 t to the minus 3 eta. Because it's less the integral, which is bound here, divided by what I have here. So the Sobolev norm cancels, and this survives here, and the epsilon becomes an epsilon to the minus 1. So, of course, I have this game to play. If I ask for too much here, then I get a not good estimate here because the epsilon hurts on the right. But it would be, so I should optimize the epsilon, and I could take epsilon equal t to the minus 2 eta. Then the conclusion is the measure of the set of points x for which let's now open the parentheses and put the definition of the discrepancy into the expression. 1 over t integral from 0 to t f of x us ds minus integral f d mu xh. The measure of set of points were this is bigger than t to the minus 2 eta, no t to the minus eta because I take the square root, Sobolev norm of f. The measure of that set is bounded by t to the minus eta. So this is saying, it looks complicated and technical, but it's saying something. Most points in xh satisfy a good error rate estimate for x for time t and the function f.
Manfred, is it needed from here that for most x's this holds for all like from a certain t and on?
Right, so then there are many upgrades that we need to do. I just wanted to not have too many
So
parameters.
this is for
around.
single t.
This is for one t. For time t. This is for one function. There are many issues with this statement right now. But it's sort of a blueprint. And you can put in more parameters in various places and make things summable. If you make things summable, you can sort of get a statement that would be true for all scale. If you put in further constants, so that here there's a 1 over n squared, for instance, popping up, then you can get a statement where for a fixed function, you have this estimate for all for the point x for all times bigger than t0, and the estimator of the points that don't satisfy these estimates for all t bigger than t0, that will be smaller than a negative power of t0. So you'd have to do that more carefully. After you did that, you want actually a statement that doesn't depend on the function. That's a bit trickier, but it's also not too difficult. I didn't plan on explaining this, but I wanted to mention that it's not so foreign, because if you prove a nice estimate or a nice statement on the torus for a character, for an exponential function, then it's very common to say, okay, but now it's also true for Sobolev functions, for smooth enough Sobolev functions. How do you do this? Well, you add a few more derivatives somehow than you had before, because that allows you to make the Fourier series summable. And if you have the statement sort of for every character with a nice error rate and the Fourier series converges rapidly enough, you can push the statement over to a smooth function. So somehow this you want to do here also. The difficulty is, of course, that we can't use characters because the space is too complicated.
Can't you use Sobolev embedding? I mean, this is going to be compact, right?
All of that uses Sobolev embedding.
The sequence of counterexamples it will converge with respect to a higher Sobolev.
Yeah, so what we do use is sort of relative traces. It's sort of a nice, cute functional analysis trick using trace class operators, and so you can probably also do it just with the full-blown harmonic analysis of the space. But it might be an overkill of what you want. And instead, what we do is and bring probably in lots of technical difficulties because we want to think of continuous functions of complex support, and then the functions that appear in the harmonic analysis, they may not have complex support, and then there are all these issues. Instead, we use relative traces in some clever way. I think Etznikov Bernstein used it in some way like that before, and we just used some ideas from that. Right. So in the end, what you get is, let me just summarize what you get. There's a lot of here in the end, because I suppose we're not doing anything else anyway. X is called T0 generic if for all t bigger than t0 and f in CC infinity x, we have with average under the orbit. Compare this to the integral with respect to the measure that we want to study, and ask this to be less or equal than t to the minus minus star. I give up. So there's some exponent here that's positive. And it should be some fixed exponent. And then this is the definition, and then the proposition that comes out of this discussion, where you need to do this more carefully, sum of all times larger than t0, and use some kind of Fourier series argument to go from one function to all functions, is the measure of the set of all points that satisfy that x is not generic is less e to the minus star. So there's another exponent that tells you that the not generic points are very small. That's what I indicated before, that somehow in the ineffective world you applied the pointwise ergodic theorem and you got a statement for a given function, and then you had sort of for this function a null set, and then you have countably many functions, and you have countably many null sets, and you need to somehow just take the union of these null sets, which in the ineffective world is very harmless and very easy to do. And you use the separability. And here we need to do these things effectively. Instead of separability, we need to do sort of this curious here, this like argument that allows us to tell how close we can get to the limit function using a finite sum, so to speak. And we need to take the union of the null sets that are not quite null sets any longer, they have just effective estimates, and we need to get sort of an effective estimate for the union. And all of that can be done, and we had to do to get to the notion of generic points. And then we went through some ideas of polynomial divergence, and somehow these statements, polynomial divergence of unipotence, somehow these things are very effective. So Ratner's theorem in general uses, if you want to just in a nutshell say what it uses generic points a lot. And what's precisely the stabilizer of the group, of the measure? That's sort of a key notion. It uses this polynomial divergence. If you sort of a parabola and you ask how fast it moves away from the origin, it behaves different than the exponential map. So parabolas, polynomials behave completely different from the exponential map, and unipotents stay polynomial and satisfy estimates that are much easier, much more manageable than what the exponential map does. So it uses this, and in the most general cases, at least in the way Margulis and Tomanov prove the theorem, it uses entropy theory. Now, generic points is sort of now effective, because this theorem, using the input from number theory, Selberg-Shackly-Langlands, or Claussel, the generic points notion is very, very effective, very nice. Polynomial behavior is very effective, that's not an issue. Entropy theory, on the other hand, is really, really something, you go to the limit and study it, as far as I see. I've seen a bit of entropy. So there's this big obstacle, how to make the whole thing effective. But in certain situations, you don't need the entropy theory. Namely, when the acting group is semi-simple itself, I found a couple of years ago an easy argument towards Ratner's theorems in the case where the acting group is semi-simple. And this is also published in the survey. It's also maybe in a book project with Tom, and you can look it up somehow. And this argument for the semi-simple case, one can make effective with these ideas, at least in the cases that we already did it. And I'm sure there will be other cases eventually. Okay, I think you all need to be done. Thank you.
Has questions?
So that should be T naught.
T-note, yes, otherwise it doesn't make sense. Thank you. Yes. Yes?
I wanted to ask what would possible applications of this effective theorem be? So what would the effective theorem give you?
So I think
effective one doesn't.
this particular theorem, even for this case that I explained, would be some statement of you have this quadratic form in the background and it may have some discriminant. And then you ask somehow, so you want to understand the values of this discriminant, of the quadratic form. What's the smallest value the quadratic form achieves in relationship to the discriminant? And that would be sort of a, you could phrase a corollary of that, yeah, in that spirit. So you have an integer quadratic form with primitive, and you have its discriminant, and you want to know what's the smallest integer value it achieves. Yeah. We also have sort of an adelic version. All of this sort of is nice, but if you know these things in the adelic world, it's even nicer for number theoretic applications. And there, I'm sure there will be more number theoretic applications from the adelic theorem that we have. But the adelic theorem currently is even more special in the assumptions than this one.
So the volume going to infinity is same as saying the discriminant of the quadratic from going to infinity?
Yeah, so that's the nice thing, that in this setting, discriminant and volume are on power scales to each other. Not just they move both to infinity, they both can be bounded by powers of each other.
Okay.
So in terms of estimates like that, if you don't care, or you stop caring because you're so bad in the exponent anyway, you stop caring about the exponent, then it doesn't matter whether you write here volume or discriminant, it's the same thing. Yeah?
So, you're saying a special case, so you took specifically SL21 in SL3, but suppose I take, I don't know, SL3 in SL4 or SL3 in SL5 or...
So if it's a maximal subgroup, the proof simplifies significantly. We didn't go as far to see that, but I wanted to just talk about the maximal case where there are no intermediate subgroups. If you have some other case which is not maximal, the question is what's its centralizer? In the paper that we've written many years ago, we assumed that the centralizer basically doesn't exist, it's just finite. That simplifies some other issues. It shouldn't play a role, except that it becomes harder to write down everything. We didn't do it yet. We want to do it, but yeah. The easy cases are sort of 80-page papers, and yeah.
When you get property T, if you take a bit bigger.
Say it again?
I mean, if the acting group was not SO21, you'd have property T. If it was a little bit bigger.
Yes, that simplifies sort of the input, but not really the output.
Simplify the
Yeah.
argument.
Thank you. Picture, right?
Yeah, thank you, Manfred.
Thanks.